This session will detail the FQ products and their performance and applications. The first presentation is entitled Evaluation of Utilizing Hydrochar Generated from TORWASH Process for the Steelmaking Industry, and it will be presented by Dr. Xuan Wang, joining us online from Sweden. Xuan has a PhD in energy engineering, which focused on reducing CO2 emissions from steel plants. Xuan now works at Swerim, where his research focus is the use of biomass residues for metallurgical applications, energy efficiency improvement, and CO2 emission reduction for the iron and steel industry. And Xuan, are you there?
Yes, I'm here. Can you hear me well?
Yes, we can hear you. The floor is yours.
Great, thank you, Mike. Yes, good morning, everyone. This is Taiwan from Swerim. I'm working at Swerim. A few words about Swerim. Swerim is a research institute for the mining, metallurgy, and material. And we are doing the industrial need research work. Currently, we are very much focused on the fossil-free and circular economy research topic. For this FQ project, we are the only one steel making representative. For the steel production, I think everyone familiar that we know about the steel, and for the steel production, it needs a lot of fossil CO2. That is because currently the steel production route is dominated by the BF route, which require a lot of fossil fuel like coal and coal, and thereby a lot of CO2, fossil CO2 is emitted. It's about 6 to 7% the whole world fossil CO2 emission. So the steel industry is facing this green transition period, and for the decarbonization process as well. And you heard about the hydrogen steel making. So by doing that, if for example the hydrogen steel making, it takes time and also it requires a large amount of investment. So there is another way to achieve the CO2 neutral. For example, we use the biocarbon in the steel making. That will play an important role for the steel industry to achieve CO2 neutral steel production. So that is why we joined this project. We really would like to see the biocarbon, how it can be used in the steel making. Right now, you can see from this slide the BF process and also the EF steel making. That is the two major steel process where we producing the hot metal and also the steel, and also from EF will be steel production directly. As for the biocarbon, it can play different roles in the process. In the blast furnace, it can be used as a reducing agent, as fuel, as stabilization, and also it supports the whole blast furnace, the burden material. As for the EF, it's besides the carbonization and also the fuel, it can also used as the slag forming agent. So obviously, the biocarbon is very important, or coal is very important for the steel making process. So for this work, we are investigating the possibility to using hydrochar generated from the TORWASH process for the steel making, and we performing the laboratory experimental work. Some key metallurgical properties and the biocarbon quality parameters are listed here, which are very important in order to use the biocarbon for the steel making process. For example, the chemical analysis and some elements which we really don't like it, like phosphorus, for example. And in order to evaluate the possibility to use, we need also check the combustibility and also reactivity. And also we need to check the safety as well when we're using the carbon. Regarding to use the biocarbon or the coal in the steel making, in principle, we can use in two ways. One way is to inject it to the furnace. We replace the coal, injection coal. The other way is we make the briquettes and then we top charge to the furnace. Where this kind of process, we need really strong the agglomerates. Because if it's not strong enough before it reacts, have this function, it will disintegrate it. And then it all is most will coming from the dust system. It will give the huge problem for the dust cleaning system, and also it has not do the function which it's supposed to do. So that's why we need also to see the agglomeration functionality. So for this project, and for our work is for the work package 2, that is in principle for the bioslab. But for us, we really would like also to see the other feedstock derived, the hydrochar. For example, this olive pomace and also orange peel. Those hydrochar, is that possible to be used as the fuel or reductant in the steel making process as well? So from this slide, you can see for the bioslab hydrochar and the olive pomace hydrochar, you can see the color compared to the orange pea. Orange pea is a bit dark and black. That means the carbonation, they have the more carbonation degree compared to the other two feedstock. And for this work today, I presented in principle is focused on the first two feedstock derived hydrochar. So I will present some major work we have been conducted. Here is the hydrochar analysis. You can see the hydrochar from different feedstock, and then we compare to the bitumen, coal, and also anthracite. So you can see for the hydrochar, in principle, the volatile content is high compared to the fossil coal, especially with the anthracite. So olive pomace has about 80% volatile content, and also you notice as well the ash content is also high for the bioslab. It's over 20%. The volatile content is high, and then you can see that fixed carbon is relatively low. For olive pomace, it's 55%, and also for the bioslab, it's about 45%. You can also notice the hydrogen content for the hydrochar is relatively high, which is good because hydrogen can be used as a reductant in the metallurgical process. And the heating value you can see here is around 20 or 21 megajoule per kilogram, and compared to the fossil coal is a bit lower. And then that is kind of explained by the oxygen content. It's high in the hydrochar. This shows the ash analysis. You can see, you can see this the ash analysis. For the hydrochar, in principle, it's a lot of calcium oxide, bioslab and olive pomace. That gives also the reason why the melting point is low compared to the fossil coal. You can see also this below temperature. Relative, it's a similar level actually as the bituminous coal. And you can also, one I point out is phosphorus oxide. So compared to the coal, anthracite is really low. So for the hydrochar, which generated from these two different feedstock, the phosphorus oxide is high. And then here it shows the some safety performance. We did the ignition points. As you can see, the biosludge hydrochar and the olive pomace hydrochar, the ignition points is lower compared to the coal, and that is indicated maybe some firing or some safety issues, and this can be also seen from this explosivity test. For the flame length, you can see the biosludge and the olive pomace is a similar level as this bituminous coal. It's about 80 centimeters or 800 millimeters. So that indicates there is some explosivity, which we need to be think about when we do the milling, because we need, especially for injection, we need to mill it. And when we have the storage, when we have this transportation period. This shows the reactivity for the hydrochar by comparing with fossil coal. You can see that the hydrochar relatively is the easy to combust. It's start combust, ignite, and combustion very early at a low temperature. And also from reactivity with this CO2 atmosphere, you can see it's compared to the fossil it's also is at a low temperature is already started reactivity, react with the CO2. And this is also actually the positive side if we talk about this blast furnace, because otherwise the coke will react with CO2 in the process gas. If we have hydrochar, it's reactive, and then it will first react with the coke. That means we can protect the coke, because the coke in the blast furnace they have the support function. So it's good that they can stay long. So that is some information regarding the combustivity and the reactivity of the hydrochar. We, of course, we investigate the agglomeration and properties. And for this agglomeration process, we usually go through the 3 steps. We design the recipe, we test it in a very small scale, and also we do some briquetting, and by different briquetting process or agglomeration techniques. And after that, we get the briquettes, and then we need to evaluate the briquettes which we generated, if this is a good quality in terms of, for example, the strength, mechanical strength, and also some others like density. And we usually do some job tests, and we also do some tumbler index. Here is the agglomeration techniques of the machines we have been using in the project. The pellet press is the laboratory scale, and we have also the technical scale, 3 types, the briquetting machine, which all is in our briquetting agglomeration lab. So we have this vapor pressure. We produce this personal, this type of the briquettes. We have roller pressure. We have this pillow-shaped briquettes, and we have also the extruder to produce this type of briquettes. I give you a few examples. For this vapor pressure, we do different types of recipes. And for example, for this one, we show the hydrochar amount, and also usually we use the cement as the additives or the binder, and we use the iron oxide and also the blast furnace mix, which from the steel plants, and also we need to control the moisture. So then we produce the briquettes, and then we do the evaluation after drying. And usually for this type of briquettes, we need to dry 28 days. So from this diagram, you can see how the tumbler index developed or grows. So you can see with the time going, this is 28 days, and the strength of this cold bound briquettes, the strength is increasing. And this dashed line, it means the required total strength by the steel plants. It's 70%. So all this fall stage drying, the produced the briquettes is actually about this 70%, which indicates it's good quality for the briquettes. And this shows the roller pressure, and this is we do different types of materials and also recipes, and this shows also the flat ash, and also we use the iron powder. So then we adding the about the 10% the hydrochar, and some we have this line, and for those for one recipe we don't. So this shows the eventually we choose to go further and to check and to produce by using this roller pressure. And we do the similar evaluation for the strength as well. Extruder as well, we did also extruder by testing different recipes with a different blending of the hydrochar and also different amount of iron ore powder. And it's we evaluated for the strength, both CCS and STS. So that is the major work which I would like to take this chance to very briefly to share with you. Some main conclusion. I should say this: the hydrochar which produced or which we get the sample from this TORWASH process, it can be a good candidate to be used in the steel making process as a fuel or as a reductant. And the hydrochar actually it has a strong combustion performance and also quite strong gasification reaction performance, which is beneficial for the steel making process. However, you can see that the hydrochar, especially the belt-large, they have the high ash content and also the high CO content. That will influence the process, and that will we may generate more slag, which will potentially have some problems. So that would be good to be considered, and it would be really good if we can remove more ash content. So that is one point. Regarding the injection applications, and as I mentioned, the ignition point is low. And there is also have the high explosivity. So that would be very important. So at the steel production side, or we have to pay more attention to keep this safety issue. We need to storage in a good way so that there will be no ignition, there is no fire, then we can use it. Another thing is also, it would be good way we can actually to blending this hydrochar with the anthracite, which has which has a high ignition point, and also it's very safe. So that will be really good to increasing the combustibility for the anthracite. So that will be a trade-off. That is good way to do in the steel production. Regarding the phosphorus, yes, phosphorus is high in the hydrochar. That's one big issue. We have to remove it, and in order to use it in the steel making process mostly. For the briquetting, yes, the briquetting, we can make the briquettes, and we can design the good recipe, and we can find the optimum ratio of the the binder amount. Either we prefer to use the organic binder, but sometimes we need to use some inorganic binder. So to increasing both the cold strength and also the hot strength. So anyway, there is a trade-off between the economical and also environmental sustainability to using the hydrochar. But we see the good potential to use the hydrochar in the steel making, and we hope we can go further. There are some dissemination we have been done. I think you can find some publication if you like, and also we can send to you for your further reading. So, Mike, this is my last slide. So, I'm done. Thank you for your listening.
Thank you, Juan. Xuan, I understand you have to catch a flight, so do you have time for a couple of questions?
One question, because taxi is waiting for me already got, yeah. But I'm able to answer question afterwards, so send me email and you can go through with Mike or Heather. I'm happy to answer your question.
Sure. Okay. So any questions from the floor very quickly? Okay. Well, I just have one online very quickly, Xuan. So just the major challenges in terms of using hydrochar in blast furnaces. You mentioned high phosphate levels, also the volatility of the hydrochar. So any other kind of major issues that you encountered?
Yeah, this is, as I said, it's major issues. But actually, this kind of issue could be handled, and it can be handled in a better way. For example, if we can extract the phosphorus, and that is as we mentioned, we know this TORWASH, there is a good opportunity to extract the phosphorus and NPK, I mean, one of these elements. So we can use it as a fertilizer and currently stage. I mean, this is a very strategic on this fertilizer issues for the agriculture and for Europe and also for all the world, which means if we can extract the phosphorus, it's good for the TORWASH. It's to make this TORWASH process more economically, and also most important, we are thinking about the steelmaking process. It would be also good for the steelmaking process. So this will be really beneficial for both sides. I think we shall go further in this direction and to make it more effective to remove the phosphorus, and then we produce fertilizer, and then meantime we can use it as the fossil reductant or fossil fuel for the steel process. Okay. I hope I answered your question.
All right. Well, thank you very much, Juan.
Thank you, everyone. Yeah. Wish you have a nice continuous conference. Yeah. Bye-bye.
Thank you. Have a nice flight.
Bye. Thank you.